Okay, so we are today going to talk about arc and angle measures, kind of looking at the relationship between the two. We already started a couple sections back when we looked at the measure of the inscribed angle is half the measure of the arc. So that's the kind of the first real result we got from it. We also saw that the measure of the central angle is equal to the measure of the arc. And we're going to add a few more things to our list. So this next theorem, theorem 8.16, says the measure of an angle formed by a tangent. So in our picture here, our tangent is this line AB, and the point of tangency is at point A, and a chord. So in this circle, the chord that we are looking at would be chord AD. Okay, so our focus here is on that angle in between the tangent and the chord. And we can find that by finding the measure of arc AD in this case. Okay, and taking half that measure. So if we take half the measure of arc AD, that's the measure of that angle between the tangent and the chord. And so we're going to look at why that is and try to make sense of that and see where we can get that from. So the rest of this picture we drew, there's a triangle drawn in the circle to help us with our proof. And in that triangle, it's indicated that this angle ACD is congruent to angle ADAB. Okay, and we need to verify that. Okay, why would that be the case? Why would those two angles have to be the same? So we're working towards that, okay? So keep thinking, try to come up with something, but I'm going to start giving a few preliminary things before that. What can we say about the measure of angle CDA? The right angle, 90 degrees. Why? AC is the diameter, yeah. And well, besides being a right angle in the circle, what kind of angle is that? Inscribed angle. And what's the measure of this arc from A to C? 180. And so half that measure is 90, and so you know it's a 90-degree angle. Yeah. What theorem does that come from, guys? The inscribed angle theorem. I think in our pack, if you page back a little bit, is that 8.7? It's the one with case 1, case 2, case 3. Okay. So theorem 8.7. So if you want to refer back to that, 8.8. Oh, it's a corollary, huh? It comes from theorem 8.7, but it's the corollary 8.8, where inscribed in the half circle. Okay, so that's something we're working with here. What else? What can we say about the measure of angle CAD plus the measure of angle DAB? In our picture here. What can you tell me about the sum of those two angles? Yes, Lena. The right angle, why? Okay, good. We have a tangent to the circle, and OA is a radius, and we have a theorem from last time we were together that the radius is always perpendicular to that tangent. What theorem was that if you look back? Eight 8.12? Okay. So we're still trying to see, well, why are these two angles congruent? we're getting somewhere here. What can you guys tell me about the measure of angle CAD plus the measure of angle ACD? What are those? Equals 90 degrees. Why is that, Chase? So yeah, this is a right angle here. It's a right triangle. And we know all three angles add up to 180, so then the other two have to be, in this case, complementary. So they have to add up to 90. Okay. And so notice the measure of CAD plus an angle is 90. And in number 3, the measure of CAD plus another angle is 90. So what can we say about those two angles that I circled? They have to be congruent, yeah. So we get that angle ACD, well, they'll just say the measure of angle ACD has to be equal to the measure of angle DAB, and we can get that through some substitution. And because the measures are the same, we could say that the angles are congruent. Right, and so that's why we see that drawn in the picture, and they're congruent by definition of what congruence means. So if you have two congruent angles, that means the measures are equal. Okay, so we're still working at, well, why would the measure of DAB be 1/2 the arc measure AD? Do we see that? Yeah, Chase? Okay, so the measure of angle ACD is 1/2 the measure of arc AD. Why? Okay, what kind of angle is ACD? And it's intercepting that arc, and so that's one of the key theorems. And then I think that was theorem 8.7 there. Okay, and so therefore, because of step 4 or step 5 here, those angles are congruent. Those angles measures are equal, and so we finally get what we're looking at. That the measure of angle DAB that also has to be 1/2 the measure of the arc AD. Okay. So we're starting to build here. We're able to use some of the theorems that we've looked at already with circles to show this. So if you have a tangent line and a chord, we can find the or there's a relationship between the angle of those two things and the measure of the arc that's intercepted by that chord. The next one, theorem 8.17, I'm going to have you do for homework. I'm going to give you a couple hints. All right. So first, let's make sure we understand what it's saying. The measure of an angle formed by two chords intersecting within a circle is equal to 1/2 the sum of the measures of the arcs intercepted by the angle and its vertical angle. So we have our two chords, DC and BA, and say we want to find one of the angles between those chords. So if we're focusing on right here, the DEA, then what the theorem says is, well, if we find the measure of arc DA and find the measure of arc BC, add those together and divide them by 2, then we'll get our angle that we're after. Okay, that's what the theorem's saying. So if I had, if this was 100 degrees and this was 80 degrees, right? And I wanted to find out what's the measure of DA DEA, then I would add the 100 and the 80 and divide that sum by 2, and I'd get 90 degrees if that were the case. Okay, so that's what the theorem's saying. How are we going to prove that? Well, what you're going to want to do is focus in on this triangle drawn here. And in particular, look at these two angles, angle BDC and BDC and DBA. They're not congruent, but take a look at those two angles. And how are those two angles related to the angle that we're wanting to know? What's the relationship between those three angles? Yeah. Well, when you add them together, right? So if you add the two interior angles of that triangle, it's equal to that exterior angle. So that's called the exterior angle theorem. And so you're going to want to use the exterior angle theorem. And then also these two angles, so if you look at the angle BDC, that's an inscribed angle. And so is the other one. And so you're going to use the inscribed angle theorem as well. And that's all you need, and you get to that proof pretty quickly. Okay, so those are my hints for this theorem, and we're going to be applying this in a little bit. Okay, so next one I'm going to do with you. Theorem 8.18 says the measure of an angle formed by a tangent and a secant which intersect outside the circle is equal to 1/2 the difference of the measures of the intercepted arcs. So you have a tangent and a secant intersecting in this picture at point P. And we are looking for a relationship between this angle P here and measures of the arcs it intercepts. And it intercepts the arc RT here, and it intercepts arc RQ, right? And to help us, we're going to focus in on this triangle that's drawn in our picture here. Okay, we're going to use the exterior angle theorem again. So if we look at this triangle, we want our theorem to include the measure of angle P, which is one of the angles in that triangle. And so if we pick, let's look at RQP as well. We add those two together. What's that supposed to equal if we use the exterior angle theorem? Which exterior angle is that equal to? Why? Which exterior angle? SRQ. Good. Okay. Then we want to solve for the measure of, so this is the exterior angle theorem. And we're going to solve for the measure of angle P. So I'm going to subtract the other angle, the measure of the other angle. And you get the measure of angle SQR minus the measure of angle RQP. Okay, is equal to the measure of angle P. Now let's take a closer look at the measure of angle SRQ. Did I write that right? SRQ. Yes. So SRQ is an angle between a tangent and a chord, right? And the one I just proved with you back here at theorem 8.16 was that same scenario, and we saw how it relates to the arc. And so we could replace this measure of that angle with the measure of which arc, or 1/2 the measure of which arc, RQ. Okay. And we'll leave the measure of angle RQP right now. And that's from theorem 8.16. And then I'm going to rewrite the first part of this. And we're going to change the second angle here. Measure of angle RQP. What kind of angle is that in the circle? It's got its vertex on the circle. It's called inscribed. It's an inscribed angle, and the inscribed angle theorem says that's 1/2 the measure of which arc? RT. All right. And that was from theorem 8.7, I think. And then lastly, to get it looking like what we have up here, we need to do one more thing. What is that? Factor. So 1/2 the measure of RQ minus the measure of RT. Okay, we got that. The next one, theorem 8.19 is one that I'm going to assign to you to do for homework. It's a little easier than the one I just did, and I'll give you a hint as well. Here we have two secants intersecting at a point P outside that circle, and we want to show that that's equal to 1/2 the measure of RS minus the measure of QT. We're going to use the exterior angle theorem again. In this case, we're going to say that the measure of angle P plus the measure of angle PRQ is equal to which exterior angle? RQS. All right. And if you look at RQS and you look at PRQ, those two angles are inscribed angles. And so you can get a relationship between those angles and the arcs, and then the theorem's pretty much proven. So exterior angle and exterior angle theorem, and then the inscribed angle theorem. Okay. And then we're going to skip ahead to the last one now. In this case, we have two tangents to our circle intersecting at a point P. And the 2 points of tangency, R and Q, if we connect those points, there's quite a bit we already know about this. There's different proofs we can show. What do you know about that triangle already? We proved it together last time. Yeah. It's isosceles. So we already know that these two are the same length. And if you look back, we actually connected R to O. We did this. We did a couple different triangles to show that, but that's an isosceles triangle. So that's one thing that can be used in our proof if we wanted to. Also, what's interesting here is if we look at arcs, if you look at the minor arc, RQ, and the major arc, RTQ, what do you know about those? They both add up to 360, right? And so that's another thing that we can use in our proof if we wanted to. What I'm going to do, though, is I'm going to use the exterior angle theorem. I'm going to work with angle P and angle PQR. And the exterior angle that's equal to the sum of those two angles would be the angle SRQ. So that's what I'm going to start with. So measure of angle P plus the measure of angle PQR is equal to the measure of angle QRS. And if I solve for measure of angle P, I could subtract measure of angle PQR from both sides. And then what can we change the measure of angle QRS to? That's an angle between what two things? QR, right here, QRS. That's between a tangent and a chord, right? And so we know that if we have a tangent and a chord, an angle between a tangent and chord is equal to 1/2 the measure of that arc intercepted by that chord. So that's equal to 1/2 the measure of arc RTQ. And then if we look at the other one, that's an angle between a tangent and a chord as well. So same theorem, so that's going to equal 1/2 the measure of arc QR. And then we factor that 1/2 out. And we get the theorem that we wanted, or the proof of the theorem we wanted. So we use the exterior angle theorem here. And we used the first theorem we proved, which was theorem 8.16. And we got 5 different results about triangles here that we're adding to our collection of results here. Questions? So out of those 5 theorems, if we take a look at what's happening in each one, we can look at the point of intersection for the angle. Is that point inside the circle, is it on the circle, or is it outside the circle? Okay, and one of the theorems applied to an angle inside that circle, and that's the first one I'm having you guys prove for homework. But what does that say about angle 1? The measure of angle 1 would equal half the measure of arc AD plus arc BC, right? Okay. So it's the arc that is intercepted by that angle. So measure of angle 1 intercepts this arc, and it's the arc intercepted by its vertical angle. And what do you know about that angle, the vertical angle? Vertical angles are congruent. So I really could put a 1 here, and I really could put a 2 here, right? So it's the 2 arcs that are across from those congruent angles. And measure of angle 2, that would be 1/2 the measure of arc AB plus the measure of arc CD. Okay. So let's apply that to a couple problems here. Go ahead and try number 1 and try number 4. And how'd you get 50 degrees on 4? Okay, so if I put x over here, so 62 is equal half of 74 plus x. Good. And then what? How'd you solve that? Good. I think that's a great way to solve this. Multiply both sides by 2. You get 124 is 74 plus x. And then you subtract your 74 and you get what, 50? And we got it. Good. Good. Okay. So there's just like two application problems to that theorem. Being able to know what it says and be able to use that. So let's skip now. So those were intersections inside the circle, right? Now we're going to look at what happens if it intersects on the circle, meaning that the vertex of that angle is you have a tangent here, and the vertex is on that circle. We've looked at one other case when it's on the circle, and we'll talk about that in a second. But this particular case, if it's on the circle, what can we say about measure of angle 1? It's 1/2 the measure of which arc? AB. And measure of angle 2 is 1/2 the measure of which arc? It's still AB, but it's the major arc, so we got to use 3 letters. So A, C, B. Okay. They both arcs have the same endpoints, but if you only use 2 letters, that's the minor arc. That's the one with the measure less than 180 degrees. You use 3 letters, it's the major arc, something bigger than. Okay. How does this formula pair up with our? There's one other one. If we have an angle on the circle and it's an inscribed circle, do we get the same kind of formula? Like if this was AB here, and we had our angle, say that's measure of angle 3, we'd say the same thing. Measure of angle 3 is 1/2 the measure of arc AB. Right? And I'm forgetting the measure on those other formulas. Okay. And so these are the cases where that angle is on the circle. So let's take a look. Why don't you guys try number 8. Allison, did you get it? Number 8? What'd you do first? Okay, good. And how'd you do that? Which is? Good. So, good. We're finding that angle using that relationship that the measure of that angle is half the measure of that arc. Good. And then what'd you do? And what'd you get? 84. So that's got to be 84 here. And that's our answer. Did anybody do it a different way? Yeah, how'd you do it? What'd you get for what's 360 minus 192? 168. Because the two arcs split the full circle, right? So they add up to 360. And then if you cut that 168 in half, you get your 84 as well. There's a couple ways to go about doing that problem. Okay. Any other ways? Or those? I think those are the only two. Okay. And then so those are angles that that are on the circle with the vertex on the circle. And then we have 3 cases where we have an angle outside that circle. Okay. Whether it's 2 secants, a secant and a tangent, or 2 tangents. But all 3 of those, if you haven't noticed, have the same exact formula. So that's why we want to put them side by side so you'll notice some of the patterns here. So in all three cases, it's 1/2 the measure of the larger arc, intercepted arc, so CE in this picture, minus the measure of the smaller intercepted arc, which in this case would be BD. And same with the second picture. Be 1/2 the larger intercepted arc, which would be BD. Sorry. Minus the measure of the smaller intercepted arc, which would be BC. And same with the third case. Okay. So seeing these side by side, these were three different theorems that we proved. Seeing them side by side, you start to say, okay, all three of those have to do with a vertex of an angle outside the circle. And we're getting the same kind of formula for all three of them. Okay. Go ahead and try number 13. Logan, did you get this one? Okay, what'd you do first? Okay, so you added 94 and 67 to go from A to D, and what did that come out to be? 161. And then you subtracted that from 180. Why 180? Oh, good. BA is the diameter. And so you're trying to find that small arc measure BD, which is 180 minus 161. That's the measure of BD. And what did that come out to be? 9? Okay. 19? Okay, 19. So you found that first, and that's a good start. Okay, and then we're after our angle, and that's going to, using the formula, that's 1/2 the larger measure, which is 67, right? Minus the 19. And what's 67 minus 19? And half of 24, we get 12. 24 was the final answer. So you got 48 here, and half of that is 24 degrees. Okay. Anybody else get 24? Okay. Any other ways? Or was that pretty much, yeah? Chase, how'd you do it? With the 180. Okay, so this is 180 over here, and then you had subtracted from 360, and you still got the 19, and then everything else worked out. Okay, good. Let's look at one last one. So skip past. Let's go to this number 12 here. We'll finish with this one, okay? Solve number 12. Okay, so on this one, you got to set it up using variables this time. And be very careful when you subtract an expression. Make sure you distribute the negative. You should end up with x is 8. And then you plug in 8 into our formula and solve that. And then you get your answer, okay? Have a good day, guys.